Oppenheimer.
Oppenheimer.
Robert Oppenheimer.
Hey there, folks. So, have you caught wind of the new Oppenheimer film that's been making waves? If you have, you are probably familiar with the tale of how Robert Oppenheimer, the theoretical physicist extraordinaire, got the nod from the US government to spearhead the Manhattan Project. You know, the one that led to the atomic bomb. But here's the kicker. Oppenheimer was no run-of-the-mill engineer, despite what you'd expect for a massive experimental project like this. A project that was started by a letter from Albert Einstein and led to the end of the World War II. Robert J. Oppenheimer was a theoretical physicist. Here's a little tidbit that might have flown under your radar. In the movie, there is a sneaky twist involving Oppenheimer's grad student, Hartland Snyder. Together, they boldly ventured into predicting the existence of black holes. Yeah, you heard that right. Those mind-bending cosmic sinkholes that munch on anything unlucky enough to cross their path. But here's the million-dollar question. Why in the name of neutrons would Oppenheimer even be noodling over black holes? Well, the short answer is that he was deep into nuclear physics, particularly the shiny new neutron particle that had everyone buzzing. These little guys are like the building blocks of atoms, but wait for it. When you toss them at hefty, unstable atoms, things get spicy. The atom splits, setting off a domino effect of more neutrons, more splits, and kaboom, you have got yourself an atomic bomb. Now, here's where things get wild. How did Oppenheimer hop from neutron squabbles to the enigmatic world of black holes? Buckle up because we are diving into some juicy history and a dash of physics magic. Zoom back to 1932, when James Chadwick in Cambridge unveiled the neutrons, these teensy particles hanging out with protons in the atomic club. And this is the kicker. Neutrons don't play the charge game like the rest. They're neutral. Fast forward and suddenly we have got a swanky atom model. Thanks to German whiz Werner Heisenberg, who cooked up the deeds. Think of a packed nucleus of protons and neutrons chilling with lightweight electrons orbiting like paparazzi around a celeb. Now, this gets more exciting cause this story takes a twist towards a whole different bombshell: nuclear fusion. Enrico Fermi and his squad were chuckling speedy neutrons at heavy atoms like uranium and watching them burst into spectacular dance of atom-splitting chaos. Imagine the pace of this scientific whirlwind from 1932 to 1939. A particle was discovered and then it started breaking atoms apart. Blink and it's 1945. And boom, atomic bombs lighten up the sky over Hiroshima and Nagasaki. This stuff was pure sci-fi gold. But it also sent shiver down the spines of both the public and scientists who saw the horrors of their experiment unleashed on the world. Speaking of scientists, James Chadwick, the neutron pioneer, found himself at ground zero during the Trinity test, the first nuclear explosion. These very experiments he started with his discovery had now morphed into this monstrous force. As for Oppenheimer, in the 30s he was more of an astrophysics enthusiast, hanging out with his buddy Richard Tolman. This guy was into the cosmos, especially Einstein's theory of relativity. Now, in 1933, the brains of Fritz Zwicky and Walter Baade fired up a whole new idea: neutron stars. Imagine stars entirely made of neutrons, like a cosmic cheese factory churning out neutron curds. Oppenheimer's interest was piqued, and he and his buddy George Volkoff crunched the numbers. They cooked up equations to figure out the heftiest a neutron star could get. Turns out, as mass packed on, gravity gets bossier. But hold up, the Pauli's excursion principle joined the party. stating that no two identical particles can have the same quantum state. A nerdy way of saying that neutrons could not be in the same space without squabbling. So Oppenheimer and Volkov wove these ideas into their calculations, revealing a magic number: the maximum mass of a neutron star. That's where gravity's crush matches neutron's resistance. They spat out 0.7 times the sun's mass, though they kind of forget about the screw you vibes between neutrons, known as the strong force. Zoom to the modern era, and we have got a better grip on this neutron star weightlifting contest. Estimates put on a non-spinning neutron star's max mass between 2.01 and 2.16 suns, thanks to slick techniques and some cosmic eavesdropping via gravitational waves. But here's another kicker. What if you push past that limit? The crush of gravity goes Hulk mode, and no neutron can hold it back. The star implodes like a cosmic shuffle, collapsing under its own weight. And just beyond this point, you cross the Schwarzschild radius, or the event horizon, the point of no return in black holes territory. You need warp speed to escape the clutches of gravity. Bam! September 1939 hits, and Oppenheimer drops a bombshell of his own, the first mathematical peek into the black hole abyss. By the 70s, the term black hole sticks, and right on the cue, in 72, we get our first cosmic snapshot of a black hole, thanks to Louis Webster and Paul Modin. So, there you have it, a journey from neutrons to nukes to the inky depths of black holes. And guess what? You are now in the know, ready to spot those physicists in Oppenheimer film. These theoretical physics wizards danced between exploding atoms and collapsing stars. It's like if Einstein had a sidekick as a rock star.